Thank you very much, Dr. Anurag, Dr. Rakesh, and good morning all, and wish you all a happy new year. So it's indeed a pleasure to interact with you all. And to be honest, if I respect the most someone, that's the teachers, because we need to understand that whatever I share with my colleagues here, okay, that sometimes restrict to them or with their students, but you are the people who are disseminating this knowledge, and you are the responsible for like creating the new generation. So first, I'd like to share my slides. So please confirm if you can.
Yeah, yes,
Can
sir.
you
We are
please?
able to see. Yes, sir. We are
Fine.
able to see.
So thanks once again. And at the outset, normally what I do, in fact, I would like to mention that there will be quite a few slides which will be very basic and introductory slides. Normally, I put in those slides whenever we have participants from different disciplines. But please do understand that many of you are having a much better understanding and knowledge in the field of energy and electrical energy and so on and so forth. So please don't feel offended. It is for the benefit of those like who belong to some other domains like pharmaceuticals and like the chemistry. That's number one. Number two, again, I reiterate that quite a few things you have a much better understanding. So please ignore and please don't take it like my ignorant arrogance to show you those basic slides. The idea is to make you aware of in this domain of energy, and to be precise, what we are doing at NEERI, which is a dedicated environmental engineering research institute. So this is how I planned my another 1 hour, 1.5 hour of things. So I'll take a little bit of advantage of this being the first talk, so we can go and look into the energy scenario and why are we worried about the problem of say global warming or CO2, despite the fact that we have such an impressive growth of solar. Then how to evaluate the impact of say energy options, which are the cleaner energy options, and then we'll move very briefly to why do we need carbon capture sequestration, because I could realize that the next talk is on uh, carbon capture by an expert. So I'll have just a bit of introduction and leave it to the next expert who is an expert of this domain. And if time permit, we'll also see that how to control the automatic emission, because there are two ways to deal with the environmental aspects of energy. One is the energy generation, which we all understand, like energy generation is impacting basically, like the global warming and environmental consequences. But equally important is energy use. If you can use the energy in a cleaner way, okay. The best example is even despite the fact you are using the fossil fuel-based energy, which is emitting CO2. If you're able to take care of the CO2, okay, during the energy use, probably that's no problem. So we need to understand that energy generation and energy use both are very important. A very brief introduction to my institute, like NEERI. It's one of the CSIR lab. We call it a National Environmental Engineering Research Institute. And obviously, as the name suggests, we deal with more or less, or I would say many aspects of environmental science and engineering. So we have dedicated groups like air pollution control group, water group, wastewater group, environmental biology group, solid waste management group. Okay, and similarly, I look after the energy and resource management group. So for further information, you can refer to the web page of NEERI. This is the kind of a brief of activities we carry out at Energy and Resource Management Division. Being at NEERI, we focus mainly on the cleaner energy use rather than energy generation. So we are actively working on the diesel emission control from automobiles as well as the diesel genset, okay, to reduce the environmental footprint. Then we work a lot on the catalysis, because catalysis is one of the things through which you can control the emissions, okay. We also work on a process called chemical looping combustion, and if time permit, I would like to give brief details, because this is one of the process for CO2 capture. Okay, and probably you will get the more details in the next talk. A colleague of mine works on the fuel cell. Then there are some problems which are specific to India, or like the developing country or less developed countries, whatever you like to call it. For example, cook stove. So you will be quite surprised that the health burden or environmental burden, mainly the health burden from cook stove or the chula is extremely high. And until a few years ago, it was probably highest among all the sources of air pollution. So in very precise words, if you talk to any experts that 4 years back, or maybe during 2015 or 16, what was the health impact from different sources of air pollution? So they will say the maximum was from chula and not from the automobile, and not from the industry. Okay, so thanks to Ujjwala Yojana, but we still have a population probably more than 25-30 crore people who are using the cook stove. So we have our own technology. We work in this area. Did some work even in Gujarat, in fact, Patan district. Then we also work on the small or informal sector. For example, small combustion devices like the tandoor, because everybody wants to work on the bigger sector, automobile and all, because there's a lot of obviously opportunities available. So we work on so-called informal sector. Then we are also working on CO2 reforming, how to use the CO2. And in addition to that, we are a part of a Clean Ganga mission, wherein we study the sediment. And more importantly for this talk, we are also taking care of energy. So we look after the energy management of our institute. And soon we will have a larger project in which we will be coordinating energy management at almost all the CSIR lab across the country. So first, let's understand about the title, and we all know that we are doing all these exercises, whether it's a cleaner energy or cleaner use of energy or resource management, to attain the sustainability, okay, or to have a sustainable development, SD, which is a buzzword now, okay. So fundamentally, it's very easy to understand the sustainable development. One of the very common definition is meeting the needs of the present generation without compromising the ability of future generation to meet their own needs. Okay, it's important to understand, because you need to, it's very easy for me to explain to you, but you need to explain it to the students, which is often quite difficult. Okay, so we are giving up fossil fuel for two reasons. One is it leads to the global warming because of the CO2 emissions, but we also know that we have a limited stock of fossil fuel. So if you go by this definition and we extract the fossil fuel, okay, indiscriminately, so we will be consuming the entire stock of fossil fuel available. So say after 50 years, you do not have fossil fuel available for your future generation. So you are compromising the needs of the future generation. That's why that's not sustainable development. Now, it's easy to say than to act, in the sense it's not easy to understand that what is sustainable and what is not sustainable. Okay, it's not easy to say that this particular process or this particular product, whether it is a plastic or it is a wood or it is even biological processes, having this much of environmental impact, and another process is having a less impact. Okay, or else there is a chemical process in an industry to generate some chemical, to produce some chemical, and you are claiming that I have made this process little greener. Okay, so we need to do it in a thorough analysis, which is typically known as the life cycle assessment or life cycle analysis. Okay, typically life cycle analysis, and many of you who are like chemical engineers or mechanical engineers do understand this topic very well. Okay, so life cycle analysis is a great tool to understand the life cycle impact of any product, any process, or for that matter, any matter. Okay, because it is known as a cradle to grave. Okay, cradle to grave. For example, you're talking about any product. So you are starting here from a raw material. Okay, you're going to the manufacturing. So when you're talking about the raw materials, suppose a mining of some ore to produce say, stainless steel. So mining of iron ore. So mining has environmental impact. Mining requires energy. Mining requires equipment. Then transportation of that ore to the industry again have environmental impact, because you are going to use a lot of sort of vehicles or train which will be using some diesel, okay, which will have other impacts. The vehicle you talk, you can easily calculate that to transport 1 ton of iron ore from mine to the industry is say 500 kilometers. So I can calculate how much of diesel I would need. I can calculate these many liters of diesel equivalent to CO2. This is just one aspect. How much of tire emissions are there? How long you are going to use that truck? After 10 years, you are using another truck. How did you manufacture the new truck? That also requires, again, mining. That also requires manufacturing. So the life cycle analysis tries to capture every aspect of any process. Then comes to the manufacturing. Every manufacturing has got energy input, other environmental input, water input. Okay, so everything is there. Then transport of your product, then use of that product, and then finally you are dumping it somewhere. How are you disposing it off? It will also have environmental impact. So every process from cradle to grave is divided into different process component, and the environmental impact or environmental footprint of every bit of a process is estimated. And then you will suddenly realize that it's not so easy, or the process which was looking probably greener. Okay, for example, this is from a Japanese companies, in fact, Yasukawa Electric's life cycle. So they are considering practically everything. Okay, like resource energy generation, how they are going to use it, what kind of logistics they need, how they are using product. Okay, and finally it is going to end of cycle. Okay, so for every product and any process, the life cycle assessment is. I have written LPG. Quick example. We all know the liquefied petroleum gas. It's a propane. So I'm using say one cylinder, which is roughly say 14 kg, okay, or 10 kg. So I know the formula of propane. I know 10 kg of propane in a month will give me this much of CO2. So I can calculate that I'm using in my kitchen one LPG cylinder per month. So my CO2 footprint of my kitchen, my cooking, anything, okay, or maybe I'm using a water heater also using LPG, is 10 kg of LPG per month, which is equivalent to say 20 kg of CO2. So I'm emitting this much. It's not that simple. How the LPG is produced? So you are extracting the crude oil. For extracting crude oil, you are investing energy. So there is a footprint. Then you are transporting crude oil from Saudi Arabia to Indian port. Again, such a long way, and then there is a CO2 footprint, there is a environmental footprint, because you are using a ship, and the ship has got a life. So after 20 years, I'm going to break that ship and produce new ship. So I need to consider that ship manufacturing also. And I need manpower in the ship. There's a captain, there's a crew. They'll be using a lot of food. Why are they using food? Just to transport my crude oil. So then there's a footprint. Once it comes to the refinery, then I'm using a lot of energy to refine the like crude and producing the LPG. So everyone understand how complex that process is. Once the LPG is produced, then I'm transporting from that Mathura refinery to say Nagpur bottling plant. Again, I'm using something, maybe truck, maybe railway. There's an energy footprint, there's CO2 footprint, and there's many other environmental footprint and manpower footprint as well. Once it comes to Nagpur, then I have a bottling plant which will fill into individual cylinder. Again, it consumes energy. These cylinders will be loaded on a truck. It is going to my dealer. The truck is using diesel, again CO2 footprint. From my dealer, it is coming to my place, my apartment. Again, I am using vehicle. And in my apartment, they are using my lift. Again, electricity is there, and electricity is produced from coal. So you can imagine that 10 kg of LPG looks so simple to calculate the CO2 footprint is not that simple. And we are just right now also ignoring many environmental footprint. Okay, so it's a pretty complex exercise, and then we realize that how much is the footprint of 10 kg of say LPG. So please try to understand and try to explain to your students what is green technology. So the question is, nothing can be absolutely green. Even nowadays, agriculture, we use a lot of fertilizer, we use a lot of water. In fact, the water footprint of Indian agriculture is extremely high. It can be reduced to the extent possible, in fact, more than 50%, I believe. So we normally say green synthesis, like the chemists who are present here. So we are replacing an organic solvent with water. So what we are doing is we are making it a relatively greener, which is a very good attempt. Okay, but we are really not talking about other things. Suppose the temperature of that process is 100 degrees Celsius or 90 degrees Celsius. So you need energy. You need a shaker. You need maybe cooling, but it is relatively greener than the previous one, which was using organic solvent. But we must understand that if we are replacing the organic solvent with water, and we are changing some parameters because it is becoming cheaper for me, not necessarily the environmental footprint will be lesser unless you do the LC. Okay, so we must try for minimum or the smart judicious use of resources, but generally in industrial production, obviously the key issue is the cost. If the cost is less, they will go for it, even if it is polluting. So that's one of the reasons that economy and the environment is always conflicting. Okay, so use of sustainable renewable sources are always promoted. For example, there are concept of green building where we are minimizing the footprint. Okay, but what is probably required is a green lifestyle, and there are a lot of initiatives. You must be seeing that in many European countries and even in India, many people are going for vegetarian diet, and they're trying to reduce their CO2 footprint. They're having a carpooling and all those things. Okay. So the message is that every process and product needs to be looked into with life cycle analysis, okay, and the green technology and sustainability approaches. And then we can try to minimize. The message is that we should not stop using anything. We should minimize it and we should try to produce it in a greener possible way. Okay. So every requirement needs to be looked into those things. Two things. One is efficient way to use it or minimum use of it, just minimize the use, and produce and dispose it in an environmentally sustainable way. Okay. So these things are quite relative, green technology or sustainable engineering. Okay. It's very contextual also. For example, the way we transport coal in India, sometimes the CO2 footprint may not be very high, but other footprint, okay, the way they carry, sometimes I have seen, there will be a lot of dust. So it is creating pollution. It will have repercussion. Okay, so it may affect your health. So their environmental sort of footprint is pretty high. So it's very contextual. Okay, it could be even area specific. It could be country specific. Okay, say you produce something in India and you produce something in US, there will be a different footprint for obvious reasons. So now, who all can contribute in this domain of cleaner technology or cleaner energy or green engineering for that matter? I believe almost everybody, especially the engineers. Okay, so chemical engineers, computer science expert, IT expert, everybody, even ENTC experts, chemists, biologists, geologists, thermal engineer, mechanical engineer. So this is an area, in fact, broader way, energy, okay, sustainability, wherein anybody can work. Okay, but this also tells us that it is highly interdisciplinary and generally collaborative approaches are very, very important. Okay? Even social science important. Now, a couple of slides, just preliminary slides that what is the impact of COVID-19 pandemic. Now we are embracing the third wave, but so far the economic activities are not slowed down for obvious reasons that we can't afford it. Okay, we have to manage with the COVID. But if you see the COVID pandemic, there was, during the first complete lockdown, there was a clear-cut reduction in the energy demand, okay? Especially the oil and coal, because there was an opportunity to use the solar. Say our power requirement was reduced by 15% and sometimes even 18 to 20%. So we reduced oil sort of consumption and the coal consumption because we know those are the dirty fuel. And we also knew that more or less the solar is coming for free. Even if you are not using it, it will be produced and wasted. Okay, so this was the scenario during 2020 as compared to 2019 when we had the first wave of COVID. Okay, and obviously when the fuel was used less, energy was used much lesser, so the CO2 emissions were also lower. So this was an evidence that the contribution to the global CO2 or atmospheric CO2 is very, very significant because of energy use. Because there are sometimes debate that natural sources are too many, okay, including the, like the animals, including the vegetation, and including the biological processes. But this was quite evident. Actually, I would say this was a very rare opportunity for environmental scientists and many other scientists, okay, to do a lot of experiments and try to validate that what we are trying to correlate based on the monitoring we do for the CO2 and a lot of modeling throughout the world scientists are doing. So if it is true, this was an opportunity where we can show and we can find out that the CO2 emissions are dropped, okay, because we started using less amount of energy, less amount of fossil fuel. So this was quite proven, okay, roughly 8%, which was quite significant, okay. And you must have seen these kind of pictures that the nature is back to its beauty and it has already restored itself. But there were some over enthusiastic sort of conclusions also, that the government doesn't do anything, and like the agencies do not do anything, and they don't clean up. The nature has done this job so quickly. It's not like that. It's a competition between the nature and human being. That how much nature has got its own capacity to assimilate and own capacity to repair. That's a fact, and this capacity is huge. But as if we are competing, okay, the nature can take care of this much of CO2, we'll try to introduce more CO2, which is like crazy, which is disastrous. So this is a very good evidence that while we are saying that the emissions were dropped by 8%, 10%, 15%, still nature was able to take care of itself. Okay, so these are the very interesting findings. And of course, the few months later, everything was back to normal, and temporary reduction in daily global CO2 emission during the COVID, they started calling temporary, and now they're back to the bang actually. Okay, so this is if you see the primary energy demand during last 100 years. Okay, so there were only 3 or 4 events during last 100 years. First was the Spanish flu. Many of us were not aware of this word Spanish flu. We got to know during COVID or Corona pandemic. Okay, then there was an economic depression, then World War II, and then finally during the COVID. So one inference is these kind of things happens only once in a while. That was a nice conclusion, that it doesn't happen every 10 years. Okay, but the second thing is, yes, these are events which may happen. So these are the primary energy demand during last 100 years. Now, if you're not from the energy domain, and if you read the news in the daily newspaper, I would say everyday newspaper, it is a bit confusing. Why it is confusing? One day you will read that India's coal import is rising. We have enough, we have too much of coal, but those coal are not clean, but we need to still import. Okay. The next day you will read something very good news about the solar. Okay. We have already attained, like 100 gigawatt of renewable energy or cleaner energy, which was better than what we have committed during the COP25, I would say, or I think 5 years back. So next day again, you will read something about thermal power plant. It's all confusing. And then next day you will read that the climate change is the reality and all this thing. So why it is so? I think when we all were kids, okay, especially I was kid, say 20 years ago, if somebody asked me what you want to do in the domain of energy, just give me 1 sec, okay? I'll just stop for 1 minute. Can somebody confirm you can still see my slides?
Yes, sir. Yes. Able to see.
So if somebody asked me 20 years back what you want to do in energy in India, so I would say that, please produce more energy so that we don't have the load shedding, especially in the rural areas. Even this scene was there 10 years ago. Okay. So load shedding and more generation of energy was the only challenge for all of us. Now, today, if you talk about the energy symbolizes pollution, health impacts, most important, climate change, regional conflicts, country's economic jerk. If the crude oil prices goes up, our economy is shaken, and so on and so forth. So energy has become very, very strategic area, very, very important area. And then we talk so much about like renewables, hydrogen, solar, and all these things. If you see the environmental, what is so-called energy environment nexus, okay, there are 2 or 3 problems, environmental problems related to the energy. One, very prominent, is a CO2. okay, which is leading to the global warming, which is leading to the, like climate change, okay. Second, which was there for ages, other air pollution. For example, NOx, fly ash problem, SOx problem, sulfur dioxide. The third problem, the waste disposal problem, okay, where we were concerned about the waste generated during the coal power production, like the fly ash and all these things. Then there were safety issues and all that. Today, probably the global warming of CO2 became very important, and at NEERI often we discuss that, look, because of the global warming and CO2 problem, people don't want to deal with the other problems. For example, the sulfur dioxide problem, which is equally important, okay? So this is the issue. Now, if you see the growth of energy demand, we will quickly see, probably we all know that India is the fastest progressing economy. Economy means energy, and energy means, of course, the CO2 footprint and the environmental footprint. Well, this is the contribution of different sector to the energy consumption. What we should see here that probably this is one of the database. Things are changing very fast. So there are some changes. So even if you see the projection of some credible agencies like International Energy Agency, today we are at 2020. We are the beginning of 2022. Okay. And the way we are progressing in solar, it looks like in 2040, everything will be renewable. We don't have to worry. But if you see the projection, it looks like the fossil fuel based or coal based or carbon based energy sources will be still dominating. Okay. Unless we have these kind of a scenario. On your right side, you can see a graph where we see the more energy, evolving transition, less globalization, rapid transition. Rapid transition means whatever we are planning to address the global warming, okay, the renewables, the energy efficiency, the clean use of energy, okay, if we go for the rapid transition and adopt those things, only then we can drop the CO2 emissions, okay. Otherwise, it's very, very difficult. In case of more energy, you can see the coal, gas, and oil will still dominate even after 20 years. Why it is happening? When we are very clear that we are at a wonderful path of a solar energy generation, biomass, hydrogen, and all these things. The simple reason for this, that today, if you need 500 gigawatt, okay, and say your share is 100 gigawatt from the cleaner energy or renewable energy, tomorrow you are targeting 300 gigawatt, or say 250 gigawatt. So now you have achieved 50% by cleaner route. But very unfortunately, now your demand is no more 500 gigawatt. It is increasing to 700 gigawatt. And after a couple of years, when your renewable energy generation is touching 500 gigawatt, and we are very happy that we are producing 500 gigawatts, all our needs are met by cleaner energy. Unfortunately, your overall energy demand will shoot to 1,000 gigawatts. And that's the reason for next 2 decades or more to come, we have no option but to probably continue with solar based energy as well as a combination of other sources, including the fossil fuel or carbon based. Okay, we will have a mix. And let's be optimistic, because if some innovation comes for the hydrogen and all that, our share of fossil fuel based energy production should go down. And that's what called rapid transition. Okay. Like 80% of the coal power plant in India and 4 Asian countries. You must be thinking India is such a bad country. Okay, we're still using coal. No, we are among the best countries when it comes to the renewable. Because we should also understand that since last 100 years, the developed nations are polluting. Okay, China polluted for last 10 years, and now they are in the path of renewables. They probably have the best growth like India in the renewables. They are probably touching 1,000 gigawatt. But when their turn was there to develop, they also polluted. Okay, so now it is our turn. And despite that, we are still using as much as possible renewables. We cannot stop coal. Always remember, whenever we are debating energy and environment, and all these are secondary thing for those who do not get enough food or enough water, or for that matter, enough electricity. So what are the priorities for them? For them, the priority is to get a good education, good food. So you cannot compromise on development. Okay, and that's why it's a very tricky, it's a very complex thing to talk about the sustainable development. And you need to actually cannot stop using coal unless you have equal amount of equal cost energy access through renewable. Because no country would like to compromise on development, and it is necessary also. It is justifiable also. Okay. So under these circumstances, what becomes extremely critical that we should not waste energy, whether in a developing world or whether in a developed world. Because when we are talking about the development that I want to feed every hungry person, I want to educate every rural kid. Okay, for that I need energy. I cannot compromise on energy. So how can I afford to waste energy by, say, excessive air conditioning or many other means? Okay. So, like not so green recovery, you will find so many such articles. Because suddenly what happens, there is a coal shortage, then we are using indigenous coal, then there is a problem of excessive energy demand. Okay, there is so many issues because we are just developing and there are so many energy requirements come in front of us. So there's a huge amount of planning, huge amount of modeling goes into that. Okay. So I'm not going to talk about, maybe there are many experts. Okay. Now, one thing is for sure that we need too much of energy. We are trying our best to produce clean energy, including the solar energy. Okay. We are doing our best. But can we look into the consequences of global warming, which is happening? Okay. Unfortunately, it is already there and it is there for quite some time. But last couple of years, we have seen it by our own eyes. So that is making an impact. Scientists knew, you also know, IPCC know. They produce report every year. They say this is happening, that is happening. But now, if we see a disaster, okay, like flooding, excessive rain, untimely rain, storms are coming, drought is there, extreme temperatures are there, agriculture crop loss is there, then we realize, okay, yeah, it is happening. Like COVID, virus is there, we can't see. When it started hitting you, then, okay, you are worried. Not everybody is worried. When it started killing you, okay, then you are really worried. So same thing happens as far as human perception is concerned. Okay, so this is absolutely there. So far what we have discussed and what is the inferences. One is the fossil fuel consumption is likely to increase for few years, and like after that it will decrease. But fossil fuel use or consumption will be there for 2 to 3 decades minimum. Unfortunately, there's no assimilative capacity left as far as air pollution is concerned and as far as CO2 is concerned. We looked into that the nature is a great sink, okay, and great healer of all these pollutants. But unfortunately, we messed up with and we polluted so much that there is no assimilatory capacity left. Every day now, it's a winter season, so every day we read that Delhi's air quality is very poor. It is again going into like a dangerous level and all these things. So there is a assimilatory capacity which we are exceeding in terms of CO2, in terms of other pollutants. Okay. Now, to understand the indirect impact, as we have seen, we need to do the life cycle analysis of everything. So there are two fundamental aspects of environmental pollution. One is the greenhouse gas emission, the CO2, CH4, and other, which is a global issue. And the conventional pollution, like the air pollution from a small industrial chimney, air pollution from your vehicle, say old vehicle, air pollution from many other things, garbage burning and all that. Then there is a water pollution issue from energy production, soil pollution issue. There are health issues, which is, say, for example, from the cook stove. These are the local issues. So let us quickly try to understand what are the CO2 or GHG emissions. Okay, you will get best of the literature, best of the slides after COP26. Okay, that what is the average warming projected for next, say, 80 years. Okay, what is the issue with 1.5 degree? What is the issue with the 2 degree? Like it's very complex thing to understand. So you need some parameters which will be easy to understand for everybody, including the scientists or including the professors like you. And then you can go into the complexity. One such issue is a global warming. And we all understand what is the greenhouse gas effect, what are the greenhouse gases like CO2 and many other gases which gets accumulated in our atmosphere. Okay, so we get a lot of solar radiation. It's coming to the earth, which is absolutely necessary for earth to keep warm, to keep biological processes happening, natural processes happening. A fraction of this heat goes back to the atmosphere. Okay, it gets trapped with these greenhouse gases, which were there, and it is required to be trapped. Okay, required to be trapped because Suppose you get, say, 100 unit of energy, out of which suppose 30 is going back. So you are left with 70, which is not enough for you. Okay. This is for your, just to explain to your students actually. Suppose you are getting 100 unit, 30 is going back, and there are some gases which is called greenhouse gases. Out of this 30, they are reflecting back, say 10, and you are getting 80, which is required for you. Now you have got more greenhouse gases. So instead of 10, they are reflecting back to the earth 20, and earth is getting warmer. There was a question, I think, to me and to many other, that you are talking about the CO2 concentration, which is roughly 425 now ppm. Suppose we are reducing it to pre-industrial level, and there is a zero CO2. Then what will happen? Whether the earth will get colder? Yes. So earth has optimized all these systems over millions of years. Whatever the gases are required, those were there. So if you increase the CO2, the earth will be warmer. If you reduce the further, which is of course impossible, it will get colder. So why a half a degree temperature makes a big deal? So biologists can very easily tell you, because most of the biochemical processes are very temperature sensitive, very, very temperature sensitive. So it can run havoc actually if you increase the temperature by 2 degrees Celsius. We have already seen there are so many coral reefs and all these things which have already been wiped out actually, even with a half a degree temperature. Especially the marine biology and practically everything gets there. Okay, like we have seen last 2 years or 3 years what has happened. Okay, so the question is, there are two questions. One is, what are the sources of these emissions? Second thing, why it is so complicated impacts, wherein we should also understand something like the biodiversity. Okay, so I'm not sure with the biodiversity we should cover here, but try to understand from some biologists that it's not easy to lose even one species, one plant species or one animal species. Okay, because it can have repercussions. It can have serious repercussions. We are not losing one species because we have got millions of species. So first, let us see what are the indirect emissions, or what are the emissions which we need to tell to our next generation, especially to the students. Okay. For example, moving or transportation. So cycle is the best. So you are cycling every day, say 10 kilometers, which is a good habit. Try to understand, if you are using a bicycle instead of a car to going to your office, you're doing a great job because you're reducing your CO2 footprint. But if you are eating too much and to maintain your weight, you are doing cycling, I don't think you are doing any good. Because if you do a mile of cycle, if you're running a bicycle for a mile, 1.5 kilometer roughly, and if you eat banana, then your CO2 emissions is 65 grams, because banana production, banana transportation, banana storage will have some CO2 footprint. If you're eating cereals with milk, it's 90. If you're going for the non-veg or cheese, it is 260 grams CO2 per mile, which is equivalent to a vehicle. Maybe a fuel efficient car will emit less emissions than your so-called exercise. Okay. So cycle is not having any emissions, but then producing bicycle, as we have seen life cycle analysis, how to produce steel. Steel itself is a whole process from mining to production, how to produce tire. Okay. So it will have its own footprint in the life cycle assessment. Then if you are eating too much and using bicycle to reduce your weight, it's pathetic. But yes, if you are using a vehicle which has got roughly 300 grams per mile CO2, and instead you are using cycle, you're doing a great job. So these are the different things which you must introduce in your college to estimate the carbon footprint. There are very user-friendly apps available to calculate the carbon footprint. And this is the right age. Rather, we should sensitize from the school days to our kids and everybody that try to estimate the carbon footprint. Okay. So by now you are convinced with the direct and indirect emissions. Direct emissions we can calculate like the LPG, and indirect emissions, for that you need to do some little bit of detailed analysis. And if you are not interested yet, those values are already available for indirect emissions. Okay. This is something to do with the water. One quick example, that to produce one shirt, you need to consume average 2,700 liters of water. because our agriculture is extremely water intensive to produce that much amount of cotton. It's okay. We need to use the shirts. We can't do it. But very unfortunately, even if you refer to this pretty old data of 2014, over 100 billion garments were produced for the first time in 2014. That's okay. Okay, we have a huge population. Very unfortunately, 60% of all clothing ends up in incinerator or waste disposal site or landfill within 1 year. So if you remember our grandfathers, they used to use one shirt for, I still use for several years. Okay. So there was a 60% increase reported in number of garments bought by an average consumer. And they
Yeah,
throw,
Nitin sir, can I interrupt you for a
yes,
second, sir?
yes,
Yeah,
please.
Smita madam and Hema ma'am, I think they have raised a hand. So I just wanted to ask whether they have some queries. Uh, if you have any queries, then you can ask at the end of the session, right? Please, ma'am.
That will be
If you
good.
have, yeah, if you have any queries, we will have a question and answer session at the
You
end.
can, yeah, you can also type in the chat box and we'll see all
Yes.
those
Yeah.
queries. Okay.
Yeah. Thank you.
So this
Thank
is
you.
one example of water footprint. Similarly, we understand that to produce a new car, we need a lot of energy inputs. So it's not easy that we calculate only the CO2 from the exhaust, which is coming from the fuel. We need to understand the footprint during the production of the car. Okay. Uh, this was a very nice example. Last year, our conference was turned into an online conference, and everybody was disappointed. But there was a calculation that, of course, we are disappointed. We could not go to the US and all these things. How much we could save 3 tons of CO2 per scientist because of this online. Or today, for example, okay, you are almost 40, 50 people, and I'm here, and we didn't travel. Okay, so it may not be making that kind of an impact because we are not having an eye contact and we are not together. That's a different thing. But today we are going to save a huge amount of CO2, which is coming through travel. Okay, so these are the efficient ways. For sure, you know all these things that these are not the things which we will lose. We have already lost them. Okay, because they could not adapt to the temperature changes or the environmental changes, mainly because of the global warming. Just to tell your students again that even if you lost rhino or you lost tiger, how does it matter to them? Or you lost, say, polar bear, they haven't even seen the polar bear. Please tell them that all these things are interrelated, which is known as a biodiversity. There may be hundreds of microorganisms living or surviving in the body of tiger, or I mean the tongue of tiger or skin of tiger. And if the tiger dies, maybe 1 or 2 or 5 microorganisms can't survive. Okay, we don't care about those microorganisms. No. Maybe those microorganisms are responsible to control the growth of some virus. So tiger gone, 5 microorganisms gone, another virus is proliferating. So these are all interrelated, which is very hard to understand, okay, which is hard to map in fact. So the best thing is to save the each and everything nature has given to us. It's not easy to say, oh, this much is lost. Okay. So please, so we need to look into the carbon footprint of all resources we consume. Okay. We need to look into the carbon footprint of final energy delivery. Okay. So life cycle assessment or life cycle analysis is a very, very useful tool to understand different energy options, different production issues, different processes. Okay. So how to reduce the overall footprint of energy? We understand for our life, we need energy. For practically everything, we need energy. So as I mentioned at the beginning of my talk, that there are 2 aspects. One is energy generation. How to do that? One is renewable. Overall clean. It should not only look clean. The way it is produced, the way it is used should be clean. It should be very efficient, cost effective, and sustainable. So energy generation should be clean, cost effective, and sustainable. So as the energy use. Again, it should be efficiently used and with minimum footprint. Okay. So you should have a good efficiency in generation, in transmission, and in use. And all put together will have a probably sustainable use of energy. Okay. So these are the word like why energy management. It's very important actually. Okay. So you need to have the generation and demand management. There are, in fact, one of my colleagues works on the AI-based tools, which can be used for possibly so-called energy islands. Okay, wherein we can imagine a village, and it has got say 2-3 sources: solar, some supply from the electricity board, which is a coal-based, some biomass-based. And there are some cold storage, for example, there are household requirement of energy, okay? And there are few processes. So we can possibly optimize the energy use and production use in such a way that we can push many things toward the renewable, okay? And maybe in a more efficient way. So today, efficiency is the buzzword. These two slides I borrowed from Dr. Sonde, who is one of the best energy experts in the country, I believe, okay? So first we should see the energy generation, okay? The reality is, did we care for the way energy is generated? If you see the power generation, the efficiency of these power generation options are in this range. What does it mean? If you are using diesel genset, so theoretically, whatever energy is there in the diesel, okay, when that chemical energy, I mean the diesel is a chemical, you are converting this chemical energy into, say, electric energy through a mechanical energy route or whatever route, we lose almost, say, 70% of energy. So the efficiency of genset is roughly, say, 30%, best of the say. Then subcritical, supercritical, or GT combined cycle, all these are for the fossil fuel-based energy generation. The energy efficiency is roughly 25 to, say, 60%. So GT combined cycle is like few plants, okay? Subcritical are there. So roughly 30% is the efficiency. Then we all know that from power plant, the energy or electricity needs to be transmitted to other feeder and from there your home. So there are transmission and distribution losses. Fine. Again, we lose 15 to 20%. So what was available theoretically to us, you almost lose 75 to 80% during production and transmission of energy produced, and it is reaching to your house. So there are opportunities for innovation. Of course, you can't like change the Rankine cycle. Okay, it's not easy. Okay, from 30% I can go to 70%. No. But the question is, or the opportunity is, even if you are able to make 2% difference, you can imagine what kind of a volume of energy we produce every day. So that innovation possibilities are there, and there a whole lot of great work is being done. So what we have seen that we have already lost about 75% or 80% of energy. Now it is reaching to your home, and we are using that electricity for different purposes. For compression, like you got a refrigerator, you have got some cooler and all these things for illumination. These are the typical energy efficiency on demand side or use side. Automobile, furnaces. Again, the scene is same. Sometimes it is 30%, sometimes it is even 20%. In cook stove, it is not even 20%. In air conditioner, nowadays we have a new generation like the 5-star and inverter air conditioner, maybe 50%. But you had already lost there almost 75%. Whatever you have 20-25%, again you are losing no less than 50%. Okay. What does it mean? We are talking so much about the CO2 which is coming from the energy, and we realize that almost 90% of the CO2 is coming from the energy wastage, which is, of course, because of some theoretical limitations, some technology limitations, but it's worrisome that today whatever CO2 is there, it is only because of the 10% or 15% of the energy used, and rest is being wasted. Now, where is the opportunity for innovation and what is the proof? So illumination is a proof. Initially, we used to use the bulb, which used to give us a 10 to 20% efficiency. Now we have even LED, okay, and very advanced, wherein you can touch even 70% of the efficiency. So you have jumped from 20% to 70%. So you are saving something like 40 to 50% of energy in your illumination today. So why not in other sector? Okay, so there are opportunities. So energy efficiency is very, very important, because whatever energy you save, that is considered as the cleanest form of energy produced, because that energy was already there, but we are not able to use it. So at NEERI, we have done an exercise. It was like our division's responsibility, and our bill was roughly 2 to 2 and 2.3 crore per year was our electricity charges. So like any other institutions, the objective was to reduce the energy consumption and also to reduce the footprint of energy. There were two basic objectives. Whatever electricity we are consuming, let's try to reduce it, use it in an efficient way. And second thing, let us try to reduce the environmental footprint of that thing. So what we all did actually, this was like a workflow identification of energy saving potential of our institute. Then basic energy audit we did, and we did a lot of data collection. And then there were two plans. One is to reduce the carbon footprint. So it's very simple. If you want to reduce the carbon footprint, instead of fossil fuel based energy, you need to generate or use the, say, renewable energy. And then we have done the cost benefit analysis that to encourage other CSI labs, okay, that how much is the investment basically, okay. So we could achieve since 2016 to 2020, I got the data that energy saving of about 20% we could do, okay. And initially we thought the payback period will be like 5 to 6 years. Where the payback period is, for example, we have replaced the air conditioners with the efficient air conditioner, okay. Then we have installed a solar-based power plant. These were the two major juggler. So this is the primary data we got from our different department. Okay. So if you can see here, the 60% of the load was from air conditioning. Everybody wants air conditioning. Sometimes we need it, sometimes in the name of equipment. Sometimes we need 26 degrees Celsius, but I like 22 degrees Celsius, which is like, according to me, it's absolutely useless. Okay, there's no reason we should use 22, 21, and 20 degrees Celsius air conditioner. So this was our load distribution. So we targeted this sector like air conditioner, and we could convince some people, yes, we can replace some ACs. Okay, it was not required. We tried to convince them. A lot of awareness campaign we did that you should use 24, 25 degrees Celsius. Okay, one very small question you should ask the people that when do you start using AC? In the winter, Nagpur has like maybe today the maximum temperature 30 degrees Celsius or 28 degrees Celsius. Do I need AC? I said, no, it's winter. I'm wearing a jacket. That means we are very comfortable in the range of 25, 26, 27 degrees Celsius or even 28 degrees Celsius. Then why do you need 20 degree or 22 degrees Celsius? Okay, so we started working on that. We have done many things. Okay, and we installed a 178 kW solar-based power plant. There was a very good RESCO model, so we could reduce the carbon footprint through this. Okay, and then we replaced 83 ACs, and we also introduced at some places centralized cooling. Just like in my division, we had a centralized cooling and a couple of ACs. So we could save at least 4 to 5 ACs through centralized cooling. We replaced 1200 tube lights with energy efficient options, replaced 480 fans, okay, it will be second level, and after 11 it will be very dim light because nobody is there. It is only for the safety purposes. So we have done a lot of interventions. Okay, this is our centralized cooling. We have a lot of awareness campaign to the people that don't use AC below 25 degrees Celsius. Okay, and through that we could have a significant amount of saving. Okay, monetary saving as well as electrical load saving. It was a little complicated for us because of COVID to understand, but yes, we had several measures to find out what was the saving, and you will be surprised that the payback period was pretty much handsome. In fact, in some cases, even not even 2 years. Okay, so this is our statistics of what kind of a solar energy generation was there and how much we can save. It's very, very attractive even today. And how much of CO2 emissions, roughly more than, in fact, 550 tons of CO2 emissions mitigated, okay, through the solar mainly. And when we introduced the other intervention, this figure doubled, okay. And today, I think we have already done, until April 21, we have done no less than 1400 tons of CO2, okay. So these are the different savings. It's a pretty attractive, I would say, proposition to even, so whatever we asked under this project, we have given back to the institute, and obviously they are quite happy. Now, in addition to that, what we are planning now under a PEN CSIR project, one is a possible expansion of solar power, because there are some innovative companies wherein they can increase your solar potential of any area. Okay, seasonal load management, energy audit, okay, and then many things. Honestly speaking, thermal scanning of the wall to sort of get like the green building, somebody is giving a lecture, so they will introduce you to what kind of a wall should be there. But there are paints available. Okay, those paints can take care of your heating. Okay, you can have a rooftop painted, you can have the wall painted. Okay, so there are different options. Again, you have the specific talks on these domains. So the typical options of clean energy or sustainable energy generations are solar, hydro, wind. Okay, many of you know that last year on 15th August, our Honorable Prime Minister announced that we have touched the 100 gigawatt figure. Okay, and everybody thought that out of 100, maybe 80 will be the solar, because we can see solar everywhere. Solar was a late enter because the solar panel were not very efficient 10 years ago. Okay, but the way India has introduced the solar program is probably the most impressive internationally. So solar at that point of time was about 45 gigawatt, and we were having more wind, okay, and a bit of a hydro and nuclear. Okay. But now solar has exceeded the wind and everything, and next 5 years we are going to have main focus on the solar. What I was trying to explain you that the different options of energy generation, okay, we need to do an in-depth analysis. So this is one of the reference I got, references are given there, that what are the safest and cleanest sources of energy in terms of greenhouse gas emissions. And please try to understand that we give emphasis only to greenhouse gases, only to climate change, then we'll be in trouble, because we need to also give importance to the health aspects and other environmental aspects. So this is the interesting slides I found, that this is the greenhouse gas emissions from coal, and this is the air pollution, which is actually affecting your health. So coal seems to be worse, then comes the oil, then comes the natural gas, then comes the biomass. Okay, it depends on what technology you are using. Not always it is true. There are biomass-based technologies which are much cleaner or much polluter also. This is hydropower, this is nuclear, this is wind, and this is solar. So you must be wondering, and now you can easily understand why the solar is having a greenhouse gas emission 5 tons, while solar doesn't generate any CO2. So this is the CO2 footprint of solar panels during its production. It requires some kind of a high temperature processes to produce the silicon wafers and all that. So solar panel has got a life of say 20 years. Okay, so you need to calculate that a solar panel produced, you have produced one panel, say 1 by 1 meter, it has emitted CO2 during its process, and that becomes the CO2 footprint for solar. But you can see the health impact of solar is very, very, very low as compared to the coal and oil. Okay, so these kind of analysis are being done under different contexts, under different new innovations in say biomass-based technology, in solar technology, in small hydro, or sometimes they call it a micro hydro or even nano hydro. Okay, and the wind technology. So it's a great opportunity. This is how they evaluate the different energy options. Okay, so availability, the environmental impact, the cost, and the CO2 impact. So this is the solar map of India. Okay, so we are blessed and we have a huge potential. Actually, it is now very high because the solar efficiency of solar panels are increasing. So instead of 750, we can easily have 1,000 gigawatt potential in India, even more, I would say. But there are many developments, many solar water heater based. I mean, this is industrial. Solar water heater at our home are very common for last 10 years or so, even more than that. Okay, but now there are industrial solar water heaters, which is becoming cost effective. These are the solar steam based system for cooking, the mass cooking. Okay, there are great developments in the photocatalytic systems. I'm sure somebody will take care of this. And this is a renewable power generation as far as India is concerned. Okay, and this is India's PV capacity addition during last 5 years, which is very impressive. I am repeating these things. So hydrogen energy is being given a lot of importance, and we have a program coordinated by National Chemical Laboratory. That's a PAN CSIR program in which many aspects of hydrogen energy is being explored. Hydrogen is being produced conventionally. How do you produce ammonia or the fertilizers? You need a lot of hydrogen. Those are produced at industrial level. But unfortunately, the process to produce hydrogen was pretty dirty. Okay, they used to use fossil fuel, in fact, or natural gas, basically. Okay, so that is known as a gray hydrogen, because it is using some carbon-based source, fuel source, which is emitting CO2. Now, what is the blue hydrogen? As I told you that why energy use is also important, not only energy production. So even if you are using the hydrogen, if you are producing hydrogen using fossil fuel, and which is generating CO2, but if you are taking care of CO2, which will be dealt in your next lecture, so the environmental impacts or environmental footprints are reduced, although your source was fossil fuel. So you produce hydrogen, you produce, the CO2 was generated, but you're taken care of CO2. So that is known as a blue hydrogen. But what is green hydrogen? You are not even producing the CO2. For example, water electrolysis. So one simple example is water is a great source of hydrogen. You can split the water into hydrogen and say oxygen, okay? And electrolysis is one common technology, but electrolysis needs electricity. So if you are producing this electricity through, say, solar panel, so your electricity is clean, and through that you are producing hydrogen. So that becomes a green hydrogen. Okay. But then you are producing hydrogen. So what is the advantage of hydrogen over the solar? Solar, to store solar, you need battery. Then battery has its own problems. Okay. So here, what you are trying to do, you are converting solar energy into electrical energy, and then from electrical energy, either you store in a battery or convert this electrical energy into back to chemical energy in the form of hydrogen. So hydrogen can be stored. So there are many research going on the hydrogen storage. You must be aware, or you may be working on that, okay, for all kinds of applications, okay. This is the global cost of hydrogen production, which is going down, quite a good revolution, and I'm very hopeful in the next 5 to 6 years, it should become a reality, okay. So this is the green hydrogen production, conversion, and end use across the energy system. I'm not going to go into the details because somebody will take these things, okay. Again, the same thing. As I told you, the CO2 intensity of hydrogen. Hydrogen is a great fuel, okay, but we need to find out how did you produce, how are you using. If you are producing using coal, it's pretty dirty, okay. If you are producing electrolysis, okay, by using solar, it's pretty. So it's easy to understand the CO2 intensity of different hydrogen options. So nowadays it's easy to even calculate, okay. So these are the given like 3 different options, gray, blue, and the green options. So I'm not going to read, which I normally hate. So the concept is there are 3 types of way to produce it. I think I'll stop another 10 minutes. Is that okay? 10 to 15 minutes I can take. Hello, can somebody confirm?
Yes, sir. It's clear.
Fine. So now we have understood that, for example, you need to produce hydrogen, or you need to produce electricity from coal, because India has got a lot of coal and it's the cheapest form of electricity available with us. So can we do something with the CO2? And I think the next talk is about the CO2 capture technology, energy efficient CO2 capture technology. I'll just introduce you about this problem, okay? So we can say the global warming is nothing but a waste disposal problem, because CO2 is a kind of a byproduct of the waste we are producing during generation of electricity or energy using fossil fuel or carbon-based fuel, okay? Now, if you want to deal with this CO2, how to deal with that? There are 2 aspects of it, okay? What is 2 aspects? One is you need to capture it. Why do you need to capture it? For example, you have a coal-based power plant. Now, the coal-based power plant is using air for the combustion of coal. And the air contains 78% of nitrogen, while our interest is oxygen present in the air. So when I'm combusting any fuel, say methane or coal with air, it will produce CO2, but it will have a lot of nitrogen. So what exhaust we get, it generally contains diluted CO2 in a typical range of say 10 to 15%. And rest will be nitrogen and a little bit of oxygen. Now, if you want to use this CO2 for any purposes, you want to produce some chemical using this CO2, you need a pure form of CO2. Okay. Naturally, if you have chemical reactions, you would expect if you have a pure form of CO2, it can be used for some food applications, for some chemical application. So first requirement or need is to pre-concentrate this CO2, which is available in the exhaust at about say 12% concentration to say 98% concentration. Okay. So for that, there are many methods which you will deal with the next section, like absorption based, or there are some advanced processes. Once you have produced 98% CO2, okay, then possibly you can convert this CO2 into some chemical, like there is a reforming process. Through reforming, you can convert this CO2 into say syngas. Now, by now, you should have questions in mind that it is fine that I'm converting this CO2 into say methanol. But the question is how I am converting and whether that process to convert CO2 into methanol requires energy for sure. Then what kind of energy is required? How are you producing energy? Suppose you need too much of energy to produce that CO2, it is of no use. Because to convert 1 kg of CO2 into methanol, if you are using so much of electricity, and in that course you are generating 2 kg of CO2, okay, come on, your CO2 footprint is more than the CO2 utilization. So these are the fantastic R&D challenges under which there is wonderful advancement, okay. And there are bench scale or even pilot scale demonstration for these processes, okay, including Indian context. India has got a huge program, and we are going to soon have a CCUS center at NEERI, Carbon Capture and Utilization Center, supported by CSIR and the industry, okay. So I'm not going to run through much of these things, or because everything is available on internet. The only thing is you should go into the credible sites. These are the sector-wise global emissions. These are the industrial target, okay? Because we have seen in one slide rapid transition. So in rapid transition, there are many things we need to do. We need to produce renewable energy. We need to improve energy efficiency. We need to do carbon capture and utilization, okay? So there are hundreds of things we need to do. And these are the things which are given to the industry, and they are responding well, I would say. Okay, this is the industry expectation from industry, say steel sector. What is short term by 2025? What is medium term? What is long term? And most of the industries are already started working on this. So these are the different options for CCUS, carbon capture, utilization, and sequestration. So we are going to deal in your next lecture. Probably it's on carbon capture, but utilization is also there. Plenty of possibilities. The only issue is how energy efficient and how clean your process is to convert CO2, okay, which is a stable molecule otherwise. So CO2 activation, sometimes it is called, sometimes it is called by different processes. This is what is known as a CO2 sequestration. So the basic difference between CO2 utilization and CO2 sequestration is CO2 utilization means you are converting into some chemical, which we have seen in the previous slide. There are possibilities that CO2 can be captured and stored. Okay, like there are reservoirs which are like the oil reservoirs. So once you extract the oil, there is some space available. Okay, so for extracting oil, you need to press something there. Okay, you need to introduce something like air or something. So instead of air, you can just dump CO2, which will be there. So that's known as a geological sequestration. So utilization is converting CO2 into useful chemicals, okay, or useful product. And sequestration means it is safely storing somewhere. But that is also, like it should be energy efficient. Otherwise, you need to transport from, say, from thermal power plant. You have some geological sequestration site, which is 500 kilometers away. You are transporting in a truck, and you are using diesel, and your CO2 footprint is higher than what CO2 you are carrying. So these are the challenges. Second thing, it should be very, very safe, environmentally safe, otherwise also safe. Okay, there should not be a leakage. There should not be the consequences of it. Okay. Well, now industry is interested, and always remember, when industry is interested, that means that there is a good future. Something is happening. So in hydrogen, industry is interested. Solar is well established now. Even in the CCUS, the industry is interested, and this is the carbon capture and sequestration market. because there will be plenty of funding available and there will be plenty of regulation or compulsions will be available to achieve the CCUS. And that's a huge market. So I remember one of my students he was intern, not my student, from a engineering college in Pune. So he was a chemical engineer, and to my surprise and pleasant surprise, he says, "Sir, I want to work on this carbon capture area." Basic, because he was here just for 6 months. I said, "Why not?" And then he got into MS admission in the Imperial College of London, where he's actually pursuing his master's in this. And he says that my professor and many professors are seeing this as a future R&D, in fact, and future technology. This is a good area to work on. Okay, give me 1 sec. I have some water. We work quite actively on something called chemical looping combustion. This is a carbon capture process. Okay. So I explained you that if you have fuel like methane, you're using air. So methane or coal plus air will give you CO2 plus a water. Okay. So as I mentioned to you, this CO2 is diluted because air contains a lot of nitrogen. So the CO2 concentration is 12%. If I ask you, instead of air, if I am using pure oxygen and burning my coal or methane with pure oxygen, what will happen? If I have a coal which is C and I'm adding O2, so I'll get only pure CO2. So I'll get 100% CO2. I need not to go for the carbon capture or CO2 capture. Okay. But to produce the amount of O2, the level of a power plant is almost impossible. I mean, we faced so much of O2 crisis, medical grade O2 crisis during last pandemic. So there's no question of producing pure O2. So there's one possibility that instead of oxygen, what we can do, we can use some metal oxides. So I'm sorry, those chemists can easily go through it, and the chemical engineers, that we can use, say, some metal oxides like this, copper oxide and nickel oxide. And we can have a bed of nickel oxide at 800 degrees Celsius, introduce methane. This methane will react with the oxygen of nickel oxide, will burn, produce the CO2. We can capture CO2, and this nickel oxide will get reduced to nickel metal. Now, in the next cycle, instead of methane, we can introduce air. Once you introduce air, the nickel metal will get reoxidized into nickel oxide. And this is an exothermic reaction which provides a lot of energy. So that's why it is known as a chemical looping combustion, because it is forming a loop. Okay. So this is relatively a new process for which we need to develop new materials, which is known as the oxygen carrier material, like nickel oxide, and we are working on some mixed oxide, these kind of oxide. Probably reported for the first time along with one Swedish lab, which is also reported during that time. So we worked on this oxygen carrier generation, okay, and then we tested it. We did a lot of typical characterization, evaluation using these kind of a steady state or fixed bed or plug flow kind of a reactor. And then we found out how much of oxygen it can carry to burn a fuel. Okay, that's first requirement. Second requirement, it should be thermally stable, obviously, because the combustion happens at 800 degrees Celsius. Then we worked on the mechanistics aspects. So we have some publications if you are interested. With one of my postdoc, I am also working in one collaborator from Saudi University on CO2 reforming of methane. So as I mentioned to you, you can convert CO2 to some useful. But the question is how much of energy you need. Okay, how much of temperature you need. Otherwise, it's useless, because if you need a very high temperature, you need electricity to generate that temperature, and you need again coal to produce that electricity. So there is a catalytic processes which can lower your temperature. So catalytic reforming of, say, CO2, okay, with methane is a very, very common topic, and you must be aware of it. So this is all about generation of cleaner energy or renewable energy, then CO2 conversion or CO2 capture. But as I mentioned to you, that energy generation is important, but energy use is also equally important. Okay, So we work quite actively on the low-cost catalyst for, like diesel emission control, VOC oxidation, or we work on the cook stove. Okay. So the buzzword is a low cost because normally the catalyst is made of platinum, palladium, which are quite costly. So we are working on diesel soot oxidation. This is how the diesel soot or diesel particulate emission particles looks under an electron microscope. Okay, this is how they are formed. Now there is a device called diesel particulate filter. So if you fix this device in your diesel car, it will trap those soot particles. So these are commercially available. It can give you more than 95% efficiency to trap those soot particles. But the challenge is after some time, this will get blocked because there will be too much of soot particles and exhaust cannot pass through it. Now, the only way to clean it is to burn it. But unfortunately, it burns at about 550 to 650 degrees Celsius, while the diesel exhaust temperature is quite low. If you go for the electrical heating, again, you have a carbon footprint, again, you have a cost. So a catalyst can possibly lower down this temperature from say 550 degrees Celsius to 300 degrees Celsius. And many people are working on this worldwide. There are, of course, commercial technologies from a leading catalyst manufacturer. So we prepare the lab scale catalyst, several number of catalysts, and then we have a 3-stage catalyst evaluation. First, we evaluate these catalysts in the lab. So we prepared 30 catalysts, we'll evaluate in the lab, then we shortlist. Okay, we evaluate under different condition, under steam and all that. Then we prepare a small scale prototype, and we sometimes use Kyushu University facility to evaluate this small scale, say 100 cc or 200 cc of prototype. And there is a small diesel engine capped here, and the diesel exhaust is diverted, and the soot is catalytically combusted. Okay, to see how efficient is this. This is some equipment I wanted to show you for 2 reasons. One is for operando or like theoretical or mechanistic studies. But more importantly, just tell your student that this is a typical Japanese university lab, and this is kind of a space is available there. Okay, so the space is luxury for us. I would say even at NEERI. Okay, they don't have space. Still, they manage it so professionally and so meticulously. Okay, so. We should encourage to our students that it's not that everything is fine there. I remember whenever I go, there's hardly 1 cylinder of helium, which at least 10 people use it. When those people come to my lab, they actually scold us. Why do you need 3 helium cylinder? For 3 things you can collect with the... so we should manage the resources very efficiently. Then we prepare the full-scale prototype, and we extensively use Professor Avinash Agarwal's facility at IIT Kanpur. Is probably one of the best in the country. So this is Indian Dynamometer facility, and now I use IIP Dehradun facility also and IIT Bhikhabhai facility as well. So you get this kind of a data that what is the particle number before your device and after your device, and the reduction in the particle number tells you obviously how efficient your device is. Okay, so. It's very important to understand. This was an article probably from IIT Bombay. The title attracted me that without green energy, the electric vehicle may up CO2 emissions in MMR by 7 to 26%. For everything we are discussing that you need electricity, okay, but if you are generating electricity through say coal-based power plant, then what is the use, okay? So it's quite debatable, and there are many aspects into this. If you are interested, we can discuss. Now at NEERI, we also try to improve the energy efficiency of some waste, related devices. So this is a sanitary pad incinerator we developed along with ARCI Hyderabad and one industry. It's one of the most efficient and very good incinerator, I would say. We have over 1,200 installations. The problem with the incinerator is it requires 800 degrees Celsius temperature. So it consumes a lot of electricity. Okay. So you need to have a device made in such a way that you need to check the energy losses, and your combustion chamber should be very efficient. Then the second thing, normally the sanitary pads are wet. Okay. So you can also design a heating cycle in such a way that we can initially make it dry, okay, with a moderate temperature of say 150 degrees Celsius, 200 degrees Celsius, and then shoot the temperature. So this is one thing. And then, as I mentioned, we work on the cook stove. We have our own cook stove, which is approved by the BIS. And the rural cook stove, जो गांव में हम लोग जाते हैं, that gives you efficiency of anything between 15 to 18% thermal efficiency. While this cook stove called Nirdhur gives you almost double, 33%. Okay, the BIS norm is 25%. So we have a few thousand installations, including in Patan district. Okay. Now this is another very important area where they are talking about the integrated energy audit and sustainability management in industry. Okay, so they want to combine all the processes. Suppose you have a refinery, so there will be multiple processes which are guzzling energy. Then there are like elimination, then there are environmental processes like wastewater treatment. So they are having an integration of all these processes so that if there is some hot water produced, can I use that energy into something? Okay, or can I reduce my wastewater inputs? Okay, or something like that. So it is done in an integrated way and it's becoming very popular. So many CSI labs start to working on that. This is my last slide. So first thing, I think you already know that energy demand is rapidly increasing because we are developing. And of course, we are also becoming some rich. So obviously, these two things are related to energy consumption. So fossil or carbon-based fuels will also be used for decades to come. And the reason I told you that despite the very, very impressive growth of solar and other renewable, we are not able to manage it 100% because our energy requirement is increasing. Now we need 500 gigawatt, after 10 we need 1000 gigawatt. Several energy options and improved energy efficiency will be important. Okay, promoting a single option can be very risky because so far we were completely dependent on fossil fuel, and today we land up in environmental problem. Today we land up in an import-based problem. Okay, so we need to keep several energy options as we understand that it's also very strategic. If you have some problem, some economic problem in the country, if you have a war, you need energy. Somebody can stop giving you energy and somebody can also stop giving you the fossil fuel. Okay, this is very important. The carbon capture, utilization and sequestration will be critical for the use of fossil fuel because we don't have assimilative capacity left with the nature or environment or atmosphere. The life cycle analysis is very important, and that too in Indian context to understand everything. Okay, it's not only about the energy generation. It's about the energy efficiency. How can we reduce it? Okay. So efficiency will be one of the keywords for sustainable development. As we have seen, there is a good possibility, and right now almost 80% of the energy, embedded energy, is wasted. There are policy issues. We need a holistic approach, and there's a very good R&D opportunities. Okay. So it's completely interdisciplinary area of research, and collaborative efforts are very, very important. This is, I'm not sure if you have seen this slide. It's a very important slide. Guspeth is a well-known name, and you know like what he says. The title is "We Scientists Do Not Know How to Do That." He used to think the top environmental problems were biodiversity, as we have seen, ecosystem collapse, and climate change. Actually, he was the president of World Resources Institute, USA. He thought that with 30 years of good science, we could address those problems. But he says that I was wrong. The top environmental problems are selfishness, greed, and apathy. And to deal with those, we need a spiritual and cultural transformation. And we scientists do not know how to do that. What very strong message. As we have seen, the environmental footprint or water footprint of those food items are so high. Like probably a water footprint of cup of tea is roughly 40 to 50 liter. I repeat, 40 to 50 liter of water. That doesn't mean you are not supposed to drink the tea. It is made to drink. But for sure, you are not supposed to waste the tea. If you are wasting a cup of tea, which costs you 10 rupees, you should also realize that I am wasting 40 liters of water. And the amount of food we waste, we all know. I don't want to talk on that. So all these are required. When we talk about the energy efficiency to save the energy, so much of energy we can save, like 80% we are wasting. Quite similar. If we don't use 2 shirts, I think we can save 5,000 liters of water. So that's very important message. I'm showing this to you because you should, inspire your students and rather sensitize your students. So I'd like to thank Dr. Anurag and Dr. the organizers for this opportunity. Thank you very much to all of you. And if you have some questions, I'll try to answer, or again, you can always write to me and you can possibly respond to also. So thanks a lot.
Thank you very much, sir. I invite, if there are any questions from the participants, you can unmute yourself and can directly ask. Or meanwhile, there is one question from Professor R.B. Varia, sir.
Yeah.
Yes, sir, he asks that to reduce exhaust emission, catalytic converter is utilized. Is there any other law for manufacturers of four-wheeler vehicles to make available replacement of catalytic converter in open market?
Okay, what I could get is the catalytic converters are used to control the exhaust emissions. Okay, is there any law to?
Is there any law for manufacturers of four-wheelers to make available replacement of catalytic converter in open market?
I think it's a very critical question, and quite incidentally, I work in this area. Okay, quick answer to this is, as I expect that you are expecting, like any other device, like tire or anything, the catalytic converter will also have a life. Okay, and after some time, it may require replacement. Okay. Very unfortunately, in India, there are no laws as such, and this is a part of what is known as the inspection and certification. In the name of I&C in India, we only have a PUC, which is not working. Okay, while in other countries, there is a very comprehensive I&C program in which you need to check practically every component, including the brake, because brake is also important for safety point of view. The tire, okay, how much are the grooves and all these things. And they do check the efficiency of catalytic converter, or if the overall emissions are more, it is mandatory to replace it. In India, so far, replacement is not available except that you got some kind of accident and all these things. But now we are working on emissions from the old vehicle. There is a ministry-sponsored project which NEERI is coordinating along with ARAI, in which we are exploring two possibilities. One is how to deal with the old vehicle, like India into now Euro 6, which is a very clean regime, very clean vehicle. But if you see, we have almost 25 kind of crores of old vehicle, which are highly polluting. So can we retrofit those devices in those old vehicles? So we are working on that. So that's a very genuine question. Okay.
Thank you, sir. And there is one more question from Professor Nimai Chandragiri. Please mention major research areas for cut down carbon footprint.
Very difficult. We need to work on plenty of areas into carbon footprint, because as I mentioned to you, one is to have a, you need to make all your production processes, first of energy generation processes, then your production processes, the carbon footprint has to be reduced, so-called green processes. Okay, so you need energy in a form of cleaner energy with minimum carbon footprint. Second thing, you need to revamp all your production processes, and also, as I mentioned to you, you need to improve the efficiency. And I like the, in fact, the title of this training program, because that's very, very important. All these things you need to do to reduce the overall carbon footprint.
So one more question is how safe is hydrogen when it comes to using as a fuel in vehicles?
Yeah, I mean, nowadays a large number of studies have been done. Initially, we thought, because even person like me, I know hydrogen because as a chemist. But for a common public, hydrogen is also something to do with the hydrogen bomb. Okay, and it's of course this very explosive process. But if you see the way hydrogen is handled, okay, it's quite safe, because there was a problem of hydrogen storage which was sorted out. There are different ways of hydrogen storage and even transportation. So it's not very difficult. And I'll give a very quick example of this. Like LPG is also pretty much explosive and pretty much dangerous. Okay, and you have seen the way we handle the LPG cylinders and all these things. So that those things have been taken care. Now it is a safe fuel. I can't hear you.
Yeah, sorry, sir. At this point of time, there is a lot of issues with waste tires, two-wheeler and four-wheeler tires. So can carbon capture possible there?
Yeah, waste tire is, like generally we call it a formal sector and informal sector. Okay, so waste tire, in fact, there are places where the tire is being used as a fuel. I mean, they simply burn, which is actually disastrous. Okay, so there are processes like pyrolysis processes which should get commercialized now to convert this waste tire into fuel, and I think there are companies which are now interested in that.
Any more questions? Participants, you can straight away, if you have any queries, you can straight away ask, unmute yourself and ask questions. So I guess there are no more questions. So, sir, thank you very much for a very stimulating session. It was a delight to hear you again, sir. Thank you from bottom of our heart, and on behalf of the organizing team and all the participants, I again thank you. Thank you for accepting our invitation and delivering such an enlightening and knowledgeable session, sir.
Thank you so much. Thanks a lot. I truly appreciate it. Thanks a lot.
Thank you. Thanks a lot, sir.
Thank you so much.